Hello, my name is Sohee Yoon, and this is my midterm problem for ME40058. So let's begin. You are Rylan Grace aboard the Hail Mary on a mission to save the sun. You have successfully established contact with an alien ship piloted by Rocky. Rocky is from planet Iridian and mainly communicates through musical chords. One day, you receive a noisy transmission, around 60 Hz hum, from Rocky's ship. Your ship's computer has free archived Iridian vocabulary recordings. What could Rocky be telling you? So in this problem, we will be given four audio files. Three of those audio files will be translated from Iridian to English, so danger, friend, and home. And then we're given an unknown signal file that Rocky sends, but it has a noisy transmission, so we don't understand what he's trying to say. So we're trying to match this unknown signal to one of these three vocabularies that we do know. This problem consists of 6 parts, and we'll be going through these parts in this video. Just to note, this is Rocky here, if you haven't seen the movie, and he's trying to send a signal to Ryland Grace's spaceship. So in part A, it asks us to load the archive files, danger, friend, and home. For each file, we want to compute the magnitude spectrum, FFT, and identify the primary fundamental frequency. The sampling frequency is 8,000 Hz. When it's asking us to identify the primary fundamental frequency, it's asking us to find like the highest peak or the greatest magnitude frequency. So let's run through the MATLAB code here on the right, line by line. So in this line, we're just going to initiate the names of the audio files that we want to run through, then initialize the sampling frequency at 8,000 Hertz, and then we're going to pre-allocate some arrays for the fundamental frequency as well as the highest frequency. The highest frequency is for part B. And we're going to run through a for loop for all the files, so this will run through 3 times because we have danger, friend, and home. Those are free files. And then we're going to run in the for loop, we're going to read the audio file and then get the signal length for normalization, and then compute the FFT using the FFT function, and then compute the two-sided spectrum magnitude using the absolute function. But then we only want the positive frequency half, so we're going to use the floor function to remove the negative portion. And then we're going to double the magnitude so that it's a bit more easier for plotting and ensuring the highest peak is found. Then we're going to create frequency axis in hertz here. In the next portion, we're going to find the fundamental frequency, so the highest peak, using the max function. And we're going to locate the index and then save that index into the fundamental frequency array that we had initialized before the for loop. And in this section, it's for part B, but we're going to find the highest significant frequency. First, we're just going to filter out some of those noises. That is like 5% of the maximum noise that we would find in the highest frequencies range. And then we're going to save the highest frequency using the max function here. And then we're just going to plot the functions here. So in the plot, these are the three magnitude spectrums, danger, friend, and home. And we can see danger is at 1200 Hz, friend is at 1500, and home is at 1800 Hz. Part B is to identify the highest frequency component in the Iridian signals from part A and calculate the Nyquist rate and determine if the current sampling frequency is sufficient to avoid aliasing. So from the MATLAB code that we had described before in part A, we identified that the highest peak is 3600 Hz from the home file. The Nyquist rate is the highest frequency times by 2, so 3600 times by 2 is 7200 Hz. In this case, the current sampling frequency, which is 8000 Hz, is greater than the Nyquist rate, so it is sufficient enough to avoid aliasing. And this equation just kind of summarizes the solution above, which is Fs is the Nyquist rate. And then if you, it should be greater than 2 times the F max to be sufficient enough to avoid aliasing. And that is the case for this problem, as we have 8000 Hertz is greater than 7200 Hertz. Now we can also check in the diagram that we had plotted in part part A, where we can see that the highest frequencies in danger, friend, and home. And home has the highest frequency here at 3600 hertz. Now for part C, we want to implement a high-pass filter using the difference equation provided below. This filters out the 60 Hz hum in the noisy transmission. Hint, use a for loop to process through the signal. So on the right, it is the MATLAB code, and we can see that we're reading the unknown signal here, the audio file. And then we're going to pre-allocate some arrays, and then we're going to implement the for loop to run the high-pass filter using the difference equation provided. And it's just going to be recursively running through and filtering out the 60 hertz hum. Then in part D, we want to find the zeros and poles of the system in part C and plot the pole zero diagram of the system. Determine whether the system is stable. So on the right, this is very similar to some of the lectures and exercises that we've done. We're going to initialize the B and A arrays for the numerator and denominator coefficients from the equation in part C. And then using the roots function, we're going to get the roots, which will give us the zeros and poles. And here we have the zero as 1 and pole as 0.9. We can actually calculate this by hand as well. And then we're just going to display the zeros and poles in a plot. So here is the plot, and you can see that the pole, the x here, is inside the unit circle, which means the system is stable. Now in part E, we want to perform a correlation between your filtered unknown signal and the free archive signals. Determine which word matches the unknown signal. Hint, use the xCor relation function to run the correlation. So on the right, it is the MATLAB code, but here we have a for loop that will run through those free files. We will read through one of the files, and then we want to run the X correlation function that they hint towards. The Y here is the unknown filtered signal, and the reference signal is the actual audio file. And we're just going to run a correlation and see how similar those files are. And that value, we're going to check the max peak, which will indicate how strongly they match. And then outside of the for loop, we have the arrays of the correlations. And we're going to see which one has the max correlation. And that max correlation would mean that that word is the most similar to the unknown filtered signal. And in our case, we find that it is the word home. Now in the final part, F, we want to plot the magnitude spectrum of the matched word and the filtered unknown signal. Visually inspect the peaks to prove your translation is correct. Note, you can also play the filtered unknown signal using the sound function and compare it to the matched word sound. So here we have this part is very similar to part A. It's more so just to understand that your correlation is correct, just to double check. And here we're just going to read the matched word. In our case, it is home. And we're going to run through the same FFT and plotting that we had done in A. So this is for the matched word, and then this would be for the filtered unknown. And then once we plot it, we should have the home, which is the matched audio file, and the filtered unknown sample here. And we can see that the peaks are relatively the same, although the filtered unknown has some noise. It looks like it is identical to home. And that's what Rocky says, home. That is the end of the presentation here. This is the MATLAB script, and here I commented out the sound function, but we can always play the unknown filtered sound to compare it with the home audio and see how similar they are. Let's run the MATLAB code. And here we have free figures. This is for part A, where we have the free magnitude spectrums, danger, friend, home. And then this is for part D with the pole zero plot, and we can see the pole is inside the unit circle. And then for figure 3, it is the final part F, and this is where we compare the matched audio file with the filtered unknown audio, and we can see how similar they are. Thank you for listening. I hope you have a great day.